Okay, so I guess we're gonna start soon. Let's wait a little bit for your people to come in. Okay, I guess that we can start slowly now. As always, if there are questions or concern, please do let me know because sometimes it's hard for me to sort of see whether I'm sort of going too slow or too quick, or whether I'm sort of like not giving sort of like the clearer aspect of the subject. As I said, we're going to spend a lot of time in chapter 4. This is about the Wickham theorem, and eventually we're going to prove the Wick. Not eventually, but I mean, one of the goals is going to be proving the Wickham theorem, which is about the class S minus that I'm going to remind you, and about the solution to the PDE, h of x du equal to c, and clearly that we have seen very clear sort of evidence between this PD and the Hamiltonian ODEs and the Lagrangian flow. And if you are curious, I mean, after we are done with this, I mean, it's going to be clearer and deeper in our lectures because we have a lot of time. But after this chapter, you can go online on YouTube. Actually, we in the PD seminar, we posted this lecture a while ago. But there's a lecture by Albert Fatih about exactly the Wickham theorem. This was at ICM 2014, I believe. That was in Seoul, in South Korea. Anyway, it was a short, not short, but it was a talk of 45 minutes. So clearly that he couldn't explain everything, but I mean, we're gonna explain things in a clearer and deeper ways because we have lots of time to do so. But I encourage you to watch this after this, or right away, whatever, whenever you have time. Okay. So I highlighted the main object here, and we have seen that there's a relation between that and with Hamiltonian flow or Lagrangian flow. And as I said, I mean, Fatih in particular gonna characterize very deeply the class S minus. And so far I have been trying to do it in a dynamical system flavor. Eventually I'll link that to the PD framework, and you see that this is quite a classical and standard object in PDE. So we can bring both of the areas together at the end of our class, hopefully. Um, so I will recall about S minus here, and that's our goal. Of just sort of a recap of the lectures, and then today is going to be deeper discussion on the class DC of TN. I'll remind you what it is. So by the way, I just posted homework problem set 1. So, again, this is a topic course. So, I mean, what I care is just that you do the problem set and make it complete and clear. That's all. You're given 5 weeks or something like that. And some of the problems already posted earlier as questions to you Problem 4 is related to today's lecture, some examples. Problem 5 is actually what we gonna prove, but I want you to reprove it so that you understand it deeply. Okay, that's all, you know, and you feel free to discuss and stuff like that with your friends. Okay, so I'll recall quickly here that we define calibrated curves. That means that it's just that, you know, it's a perfect curve of action functional that if you reach any, you know, you have, this is a calibrated curve gamma, then what it meant was that if you take any point like gamma t to, you know, let's say that the curve is parameterized this way to gamma t prime, then you would have that u of gamma t prime, the difference in values at the two endpoints equals to the action, normalized action, if you want to say it like that, because it's a c. Okay, that's it for any interval t primes in R. That's all. Okay. And what is remarkable here is that we are going to use the calibrated curves together with you know, earlier definition we defined to define Wickham solution of negative types. As I said, I mean, in order to avoid confusions, I'm going to mostly focus on Wickham solution of negative types. The one for positive type gonna go in a similar manner, so I don't want to confuse you between the two and, you know, get things twisted. So we are only focusing in this class on S minus. So this is, you know, Wickham solution of negative type. And by that, we meant that there are two properties for it to hold, right? First, that U is dominated by L plus C, you know, that is for any eta absolutely continuous from any AB to the torus, you have, instead of you have the equality like above, you know, for calibrated curves, you only have that is being dominated, right? So you only have U of eta B minus U of eta I. It's less than equals to the action functional. So that's what meant by being dominated by that. Okay. And the second one is rather geometric and interesting. This is really remarkable. I mean, we're gonna get to this point, and it's actually related to the differentiability of U. Again, it's gonna take us a while to get there. Second property can be viewed in a very geometrical way, that if you take any point X in the torus, you're gonna be able to find a calibrated curve going from minus infinity ending at 0 at x. So you would have gamma 0 equals to x, and gamma going from minus infinity 0 to the torus is ULC calibrated. Remember that we automatically have that gamma is in CK. Actually, I think Sun asked the question last time that, you know, calibrated, does it imply it's an extremer or a minimizer? That it is, I mean, provided that you have the fact that U is dominated by L plus C. Okay, so those two together gives you that. So negative types here just meant that you are going from minus infinity to 0. That's what it meant. So it's a array, right? I mean, and again, I mean, in the PD language, people say that gamma is a backward characteristic, you know, ending at X. So this is a little bit confusing always for me. I mean, by what we say ending or starting, whatever. I just meant here that gamma 0 equals to X, okay? And backward characteristic is very important. You're gonna see later on, okay? So you see that there are 2 points here, right? I mean, okay, and then let me also recall the definition. The definition that we defined was that I don't know. I just respect the notion of party. So sometimes it looks a little bit confusing, but dominated here is dominated normalized by C. So DCTN is a set of all function U continuous function. So remember that we only require U to be continuous here. Okay. And then U is dominated by L plus C. Okay. So why is this important? I mean, this is important because it's part of the definition above here, right? I mean, this one is part of what was used here, right? So that's why. So I mean, our goal is to really characterize the set S minus, right? That is a set of Wickham solution. And again, we're gonna talk about dynamic after this once we understand Wickham theorem. I mean, deeper dynamics. Okay, so the goal is to characterize S minus, and you see that S minus first require the function to be dominated by L plus C first, right? And then the fact that there exists an, like backward characteristic or calibrated curve comes later. So to do this, we first need to characterize the set DCTN, right? So that's gonna be our goal. That's what I meant from the beginning. So we're gonna try to go in this lecture and the next to characterize what's the set of all dominated functions on the torus first. And then from here, we're gonna go further to, characterize S minus. Okay, and that's exactly what was on the left panel here. I mean, I recall everything on the left panel as well. Okay. So again, from the definition, we only require a priori, that U is only continuous, right? So we don't even require any differentiability of U, because if you look at the definition, I mean, I wrote it earlier, but you can also look into the definition on the left panel that I'm highlighting here. It's only involving the difference of U, so U only needs to be continuous. Okay. So, it starts quite abstract. So our theorem for today, our main theorem for today. So today's main result gonna be that if U is in the C of Tn, then we would be able to conclude that U is actually better than being continuous. So U is going to be Lipschitz in the torus, and H of x du x is less than or equals to C almost everywhere in the torus. Okay. So, and again, for those of you who are not yet too familiar with the notion of Lipschitz property, it is just that Ux minus Uy is less than or equals to C times x minus y for all xy in the torus. Okay, or you can also view it as a function in Rn that is Zn periodic. That's our main goal for today. But before that, let's prove a rather simple lemma that was written on the left panel. And this also answers some of your earlier questions about characterizations of things, right? And this is exactly what we are doing. So we start characterize things. So we say first that if U is in DCTN, then so is U plus C for any constant C. Okay. This is simple, but you can see it right away from the definition, right? Because if you have U of gamma B minus U of gamma A, this is the same as you take U of gamma B plus a constant minus U of gamma A plus a constant, right? So that's why the first part is obvious, right? Again, I mean, I'm only using this definition that is given to me, that, you know, if I'm taking any curve, then I have this red box. I'm not yet using any property, right? This is purely about comparing values of a continuous function at the two endpoint with the action function, right? This is not yet anything about PD. It's kind of Lagrangian framework, right? You know, okay. Um, so I have to base upon that definition to prove anything, and you see that the first part is obvious, right? The second part of the lemma is that the set is closed and convex subset of the set of continuous function. Okay, so by closeness here, I meant that if we have a sequence UK that is in the space of continuous function, uh, intersect, oops, hold on a sec, uh, intersect with DC of the torus, and UK converges to U uniformly in Tn, then we should have that U is also in DC of Tn, right? Again, this is also obvious because you would take any curve, you would have UK gamma B minus UK of gamma A is less than equals to the action functional, normalized action functional on gamma. So L gamma dot plus C ds. Okay, so sometimes I would write to be C times B minus A, or sometimes I would put C in the action set. Okay, and you see that this action function is fixed, right? So you let k goes to infinity, you would end up with exactly U gamma B minus U gamma A less than equals to that. So that allows us to conclude that U is another member in this one. So the closeness property is clear. That's what I meant here on the left panel, and I just gave you the proof on the right panel. And same for convexity. For convexity, it meant that if you take any two function U and V in the set of DC torus, you know, you just take the definition here, and then you would take a convex combination of them. So W is SU plus 1 minus SV, you know, and just a normal convex combination allows you to see this property right away, right? So you conclude that W, which is SU times S times U plus 1 minus S times V, also is in DCTN. Okay. So I mean, those two properties are rather interesting, but quite elementary, right? What is one of the, you know, remarkable and important property here is that you can conclude the red box here, the third item on the lemma, that you know, if U is in DC of Tn, and U is automatically Lipschitz. Okay, so that's remarkable because, again, if you look back into the definition, it doesn't say anything about that you need to have any sort of Lipschitz property or any gradient bound, right? But as you have seen, I mean, we have actually also done this last time, you know, in order to explore the differentiability of U, you take, you know, or in order to explore the boundedness of the difference of Uy minus Uz, right? So you take 2 points, Y and Z. So let me try to follow my notions. You want to compare the values of Uy with Uz, right? Or you want to estimate the difference, or estimate Uy minus Uz, right? That's a natural question to ask because you are allowed to design any possible curve that you can. And in particular, I mean, a natural way to connect two points, just to use, you know, like line segments, right, of any fixed speed that you can think of. I'm here choosing constant speed, 1 unit speed, just because, you know, just because of the um, you know, normal way that people would do. You don't have to fix it to be unit speed, but you know, we just connect y to z by a line segment of unit speed, right? That's what we are doing. Of course, I mean, we can assume that y is not z here, otherwise there's nothing to worry about. And if you do so, you can write out, you know, precisely your parameterization of your curve gamma, which is starting at y. You go with unit speed in the direction of z minus y. So s times z minus y over length. So this is unit speed for s going from 0 to the length. Again, you know, you don't need this constant unit speed. You can choose different constant speed. So if you do it like that, then by definition of the boundedness, you have, I mean, or of the dominated, you have uz minus uy is less than equals to, no, equals, no, it's okay, less than equals to the action functional, right? Integral from 0 to z minus y of L of gamma s, gamma dot s ds. So you see, it's very elementary. Everything is built upon, you know, very simple ideas. But, you know, once we have done a lot, then we have a very good theory, or I mean, good setup tools. Okay, and you compute this one, you see nothing but just z minus y. L of gamma is something. You can just keep it L of gamma. I mean, I don't even need to bother to write out gamma because gamma is just in a torus, right? So it's bounded. Uh, Again, if we are dealing with something non-compact, then we have to be careful, right? I mean, so Wickham theory for non-compact setting might be really challenging. Um, if I take gamma dot and it's just unit speed, z minus y over z minus y. Yeah, so you see that this is bounded, right? So you just see that this is bounded by c times z minus y, where z is, sorry, c can be chosen as what? As the maximum of lyv, right? You just guess, right? I mean, y is always in the whole torus, doesn't matter. You can say v is having speed only 1, or you can be more generous to let the length of v is less than equals to 1 or something, okay? Why would I write c is that plus c? Oh, I'm sorry, I'm sorry, I missed the little c. So there's a little c here, the normalized constant times the distance, z minus y. So there should be c, z minus y, okay? So less than equals to that, so I should have big C is this one plus the little c, okay? I'm sorry about that. So, and then by a symmetric argument, right? So we are able to end up with the fact that we have uz minus uy is less than equals to this constant times z minus y. Okay, so we are done. Um, so, you know, this actually demonstrate one thing that although you might think that this requirement of u in DCTN is not a lot, but it turns out to be a lot because it asks you to verify this one for any possible absolutely continuous or piecewise C1 curves, and there's a whole, you know, like universe of those curves, right? You know, so uh, asking you to be in DCTN seemingly is rather complicated, and that's why that, you know, if we leave it like this, and then it wouldn't be too nice to understand what's DCTN. Okay, again, bear with me. It's quite elementary in some parts, but overall, I mean, again, once we have built enough of the tools, and it becomes really remarkable. And ask me questions or discuss with me if there's something unclear or something that I'm making mistakes or typos or something like that. It's very highly likely that I can make some. Okay. Again, so this is the main result for today. We have proved the first part that U is Lipschitz. Okay, that was the first part that we proved. And surely, I mean, when it's Lipschitz and it's differentiable almost everywhere by Rademacher theorem. The second part that I want to prove today is that at any point of differentiability of U, we have this inequality. Okay.
Can I ask a question about that statement?
Yeah.
So when we say almost everywhere, that's just the almost everywhere set of points where the differentiable, right? Or is
Yes.
there an extra? Are there certain differential points where that are not, they don't satisfy the inequality, or?
Yeah. Thanks for the question. Yes. So that has to be made clear. So almost everywhere here. Okay. So actually, okay. So remark. So when I write down h of x du of x, right? Then the clear question is what's the meaning of this? Right? If U is only Lipschitz in Tn, right? So that's the first honest question that we can ask. So in fact, du of x, the classical gradient only makes sense when we are at the point that U is differentiable, right? So clearly, h of x du of x only makes sense when U is differentiable at x, right? So the question you asked, surely that we can make it clear that like what I mentioned here, that at points of differentiability of U, then this makes sense and I have this inequality, right? So that's a clearer way to say it now. But also that when we only say that, say, U is Lipschitz in the torus and h of x du x is less than or equal to c almost everywhere x in the torus. So I mean the two statements look the same, but this is stronger than that, right? So this is stronger and this is weaker, right? Because the stronger statement was clearer because that is only happening, or that's happening at the point of differentiability of U. When I write the statement on the right panel here, it's weaker because I'm not requiring clearly at what point for almost everywhere x in the torus at that I have that inequality. But my point here is that they are only differ by a set of measure 0, right? So because for the later one here to make sense, we also need that du x exists, and almost everywhere here can be smaller than almost everywhere above, right? But and the two boxes can differ by a set of measure 0, Low-back measure 0, but this doesn't matter. Okay, we're gonna see this. Okay, now but clearly that we need to make it very clear, and the theorem or the main result here is stronger, right? It requires that it has to be correct at any point of differentiability of U. Okay, I hope that that's clear. But eventually we're going to show that even the weaker version or the stronger version, they're going to be the same, so that wouldn't be a problem, because once we ignore a set of measure 0, when we do integration and stuff like that, we wouldn't care, Okay, that would be the you know the the big picture for this kind of question. Okay, so thanks for that. All right, so let's see. Um, yeah, actually, the proof, if you think about it, it's also going in the similar manner like what we did last time as well. It's always that, you know, so this proof that we are doing, so proof on the left panel. Uh, this is kind of, I would say that although it looks very simple, but this is a quite general proof for this kind of statement. And for uh, for dynamic programming principle implying PD result, um, in general, in optimal control in general. So keep in your mind this proof. You might actually end up using them later on in a totally different context, like it's a very simple thing because the key point is always that you need to go from certain action functional, certain integral formulations, right? You need to go from there to PDE, right? To go from there to PDE, it's always natural that you would need to end up with, the gradient, the Hessian, or anything with respect to derivatives, partial derivatives. And in order to do derivatives, we have discussed this last time. You just do this part that I'm highlighting here, that you are trying to, from the points x of differentiability. So you have U is Lipschitz, right? So by Rademacher theorem, you implies that U is differentiable almost everywhere. So you take x to be a point of differentiability of U, right? That is, you have du x exists, and when it exists, then that means that if you take u x here, you take a point x here, and you try to make sure that you go from the values of u to the derivatives of u, then you can just explore along any possible directions you can go, right? For example, if you explore it along the directions of x plus tv, then it's just a natural thing to write down that limit of t goes to 0 plus minus, doesn't matter, u of x plus tv minus u of x over t. This is du x dot with v, right? Or you can write d del u over del v at x. It's just the directional derivative in the v directions. So this is very simple, but it's a universal idea that whenever you go from action functional or certain integral identities that you want to go back to a PDE, um, then that's the way to go, and it occurs in many different application across many different fields. Okay, so that's how it goes. Okay, so let me go back to the lab panel here, and we are doing exactly the same thing, right? So we are trying to make the derivatives occurs, and let me highlight here what I just wrote down. So the rational derivative in v is this limit, right? So that's what we want, because that's the only way, well, not the only, one natural way to connect from the difference in terms of value at 2 points to the action functional, right? So indeed, you take this curve gamma to be x plus sv for 0 less than equal to s less than equal to t, and then you just write down the dominations definition. This is less than equals to that, just the, okay. And then same game all over again. You take the limit, divide both of the sides by t, and you would end up with this red box here. Um, so it's just that, right? So you would have dux dot with v is less than equals to lxv plus c. And now you just write out the definition of the Hamiltonian. So you have h of x dux is just supremum of dux dot v minus lxv. So this is less than equals to c. Okay, so we are done. So we would have h of x dux is less than equals to c whenever u is differentiable at x. Okay. And believe me, I mean, I really mean this when I say that it occurs in a lot of contexts. When you write down something like large deviation properties from probability, then you would have that it satisfy certain either rate function, satisfy certain PDE, Hamilton-Jacobi equations, or also from economics, there are certain problems that when you want to derive the PDE, then this is the way you go. Okay. Now, any questions or concerned about this? And then I have exactly a good amount of time to let me pause here for a few seconds to see if you have questions. I have exactly a good amount of time to discuss with you some examples. So, and also, I'm sorry if this sometimes is a little bit abstract because there are certainly not a lot of examples, and then I'm trying to bring up examples whenever I can, and it's actually quite interesting. Okay, so if there's no question, then we can move forward now to this next example. So I mean, in the post-homework problem, I'm just asking you to give exactly one more example of this kind, and we are gonna checking things directly. So I mean, after the next lecture also gonna be quite light but intuitive, that we're gonna be able to characterize the whole DC of Tn. But for today, at least I want you to think about real examples that for example, the case we are considering here is that we are in one dimension, and we are in a homogeneous media. By this, I mean that there's you can say that there's either no potential energy, or you can say that the potential energy at every place is the same. So homogeneous media, that meant that the Hamiltonian is independent of space, independent of the spatial location. So it's only just the classical mechanics Hamiltonian, but just 1/2 p square, and there's absolutely no changes in the potential energy. So you can think so here the potential energy just 0. Okay, and I'm writing down here that C is 1, but I mean, you can think first that so C is going to be the energy level, right? And clearly that if you here's only 1/2 p square, right? So the energy level in this case should be always greater or equals to 0, right? Because if it's less than 0, then it wouldn't make any sense, right? Okay, and again, I mean, the torus is just r over, oops, torus is just R over Z. Okay. So because I'm in the note here, I'm only asking you to think about D1 of the torus, but in fact, we can think about general situation, right? So when C is 0, the easiest case, then you see that everything should be 0, right? Because the Hamiltonian is 1/2 of P squared. How do we see it? What is the D0 of T, right? This is or U in the continuous function, C of T, so that I have U is less than L, right? Again, yeah, I should have said that if the Hamiltonian is that, then I should have L of XV is 1/2 of V squared, right? Okay, so there are many ways to see D0 of T. How do I see it in the how do I see it in the clearest way? Well, okay. So we just proved, right, that U is in DC of T, then it implies that U is Lipschitz. Again, this is not yet if and only if, but U is Lipschitz and U satisfy at differentiable points of U that H of X du X is less than or equal to C at differentiable point of U, right? So you use this result for C equals to 0. You write exactly like that. So U is in D0 of the torus, implies that U is Lipschitz, and you satisfy at differentiable point of U that H of X du X, this equals to 1/2 of du X squared, less than or equal to C, which is 0, right? So if that is the case, the 0 energy level, then you would imply that dux equals to 0 almost everywhere, right? And that helps us to conclude we have a full characterization of D0 of torus that helps us to conclude that U is a constant function, right? Of course, if you check back, if it's you have a constant function, then it automatically satisfies the inequality, right? Okay, so this is the full characterization of full characterization of D0, the torus, right? And now you realize that actually when you consider C is 1, this is going to be the same as C greater than 0 for any fixed C, right? Because again, it's just just differ in this case. I mean, in general they might be very different, but in this case, in a homogeneous media, then I mean they are the same, of course, up to certain normalization. Okay, so that's why I want to just think about C equals to 1, and the reasoning was that we already proved that U in D1 of the torus implies that U is Lipschitz, and at differentiable points of U, we have that H of X du, which is 1/2 of du X squared. Okay, now I see that I might make a okay, fine, I'm gonna correct it. I might make a mistake here. So this is less than or equals to 1. Okay, so I guess that almost everywhere, right? So this implies that you would have dux, which is in this case 1d, right? So u prime of x is less than or equals to root of 2 almost everywhere, right? So you see that you allowed your functions to have slopes at most, going from minus root of 2 to root of 2. Yeah, so you go back here, you see that the first thing gonna satisfy, right? A constant function, then surely its slope is gonna be just 0. and it surely satisfied, what we are talking about here. Clearly, this doesn't yet imply that u is in D one of the torus, right? But you can verify if u is just a constant function, then it satisfies the above, but not yet in D one of the torus. But you can verify by definition that you have u of gamma b minus u of gamma I for any gamma. This is just going to be 0, right? And surely this is always less than equals to the action function of from A to B of L of gamma dot plus C ds. Why is it so? Because you just write it down, right? So C is 1. This is just integral from A to B, 1/2 of gamma dot of S plus 1 ds, and this is always greater or equal to 0, right? So we are done. So that the first part was easy, and I think I'm making a mistake here in the second part, that ux is this curve, and the reason why I'm saying that no, I take it back. I'm still correct. No, I take it back. Actually, I'm correct. Okay, I'm not. No, I'm sorry. I'm not making a mistake. It's just correct. So here the second example I'm giving you is that u has slopes plus minus 1 at points of differentiabilities, right? I'm sorry about that. It's a correct example. It's just not the sharpest one. So you see that you have slopes plus minus 1 at points of differentiability. So if you come here, you see, okay, there's nothing wrong, right? Because it satisfied these conditions. Again, we haven't proved that the converse holds. So even if it satisfies the conditions that I'm highlighting here, it doesn't yet imply that U is in D1 of the torus. But let's prove it, okay? So, oops. So the second example, we're gonna verify directly that U is bounded by L plus 1, okay? How do we verify it? Okay, let's see. Let me draw a curve, and you see that this is start getting interesting because suddenly you have a bunch of varieties of functions. So you just need your function to be continuous having slope plus minus 1. I don't even need to write down what's going to be the value, but here's what I care about. So if you take any curve going in the R, let's say that you have this is the starting point. Give me 1 second. So you can say that this is your gamma I, and you go, along this part, you can go back and forth, doesn't matter. You might end up with this is gamma B. Okay, so let's just write that. Okay, so what do I have? I have u of gamma B minus u of gamma I is something, right? But what's the strongest value? I mean, what's the highest value that it can go? This should be less than equals to gamma B minus gamma I, right? Because again, U has slopes plus minus 1. The best it can go is with slope always 1 or always minus 1, right? So this is at most that. So let's assume that with the loss of generality, that is equals to gamma B minus gamma I. Okay, again, I'm just assuming that gamma B greater than gamma I, or else you can do the same. Now, on the other hand, you can just do a simple sort of like Cauchy-Schwarz inequality, if I'm not mistaken, ds. This is going to be greater than equals to integral from I to B. Just using Cauchy-Schwarz here, it's going to be greater than equals to 2 times root of 1/2 times gamma dot of SDS, right? So this gives us that this is root of 2 times gamma B minus gamma I. So it's clearly greater than gamma B minus gamma I, and clearly greater than equals to, oops, what I'm doing, greater equals to U of gamma B minus U of gamma I. Okay, so we are done. So in fact, from this proof, it's really interesting. Later on, we're going to have the whole characterization of functions like this in a really general way, but for fun. I mean, this is not in your homework problem. Your homework problem is simpler. From here, can you directly characterize all DC of the torus? What do you think? Can you characterize all of those, or I mean, yes or no, or maybe I'm out of time? But I mean, you can think about that just for fun, or you can discuss with your friends. This is, again, to me, it's really remarkable because we are, you know, talking about very simple example, but we see really deep properties of things. And for the next lecture, again, we're also going to go slowly, but we're going to show the converse. So we're going to show that if U is Lipschitz and satisfy this property almost everywhere, then it implies that U is in DC of Tn. So in other words, we have a complete PD characterizations of the set DC of the Tn. So that's, you know, and then we're going to start discussing something from there. So any questions or concerns or comments? Okay. 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 Other than that, then thank you all again. My goal for this class is that I'm, as always, trying to convince you that eventually a rather complicated topic, really modern, can be broken down into simple pieces. You might see that I am repeating myself quite sometimes for various sort of ideas. And some of them might seem really simple, but believe me, I mean, most of the simple ideas, once being used in a correct way, gonna be remarkable. And again, you know, if some of the beautiful ideas can be carried with you in your research or in whatever things that you are using, I'm very happy. That's all. Okay. Other than that, then have a great weekend. I'll try to post the next lecture notes in a timely manner, and you know, stay safe and healthy. Hopefully that, you know, things are gradually getting better, hopefully. Okay, so thanks for now. Thank you. See you.